Hello and welcome to my AP Chemistry students. I'm going to try this out. I'm not good at technology, but I'm going to do my best to post a little lecture section about acids and bases. So to make this, familiar, get us back into the groove of things, I'll ask Andrew to take his sweatshirt off at some point during the lesson. I'll tell Luke to stop saying inappropriate things at some point during the lesson, and Joe stop playing video games. Okay, perfect. So we're going to talk today about a few different things. Gotta go fast so that this video can be uploaded. I want to talk about acid bases writing their dissociations. We'll try an equilibrium problem. Then we'll talk about Ka, Kb, Kw, pH, POH. What's pKa? What's pKb? Lots of units. We'll look at key relationships in conjugate acids and bases and in solutions. Okay, so I'm going to erase this and start working on things kind of one by one. First thing that we're going to look at is the idea of dissociations. Okay, so when we're talking about acid-base dissociations and writing them, this is part of your homework. If you have, for instance, acid, hydrochloric acid, in water, H2O. When you show the dissociation of the acid, you'll just show basically the hydrogen jumping over to the water, right? And then we can label your acid, the water in this case would be a base. This becomes the conjugate acid and the conjugate base if the reaction proceeds to the left. Okay, if you want to write something like this for the dissociation of a base, if it's like a Bronsted-Lowry base, something like ammonia with water, right? What's going to happen is it's going to accept now hydrogen from the water to be NH4 plus OH. So here you have your base. Water in this case is the acid. This becomes the conjugate acid and the conjugate base. Because going backwards, that hydrogen is going to go backwards. So that's writing dissociations. Some, if you have, for instance, an Arrhenius base, like sodium hydroxide, you wouldn't necessarily write with the water. What happens with the sodium hydroxide is the sodium and the hydroxide just dissociate, as you'd show like a solubility problem, or something like that. You can also do the same thing with acids if you want. You can write the dissociation of hydrochloric acid without the water this way. And as, I'm sorry, not that way. And as we discussed, the hydrogen ion is the equivalent of the hydronium ion. They're really the same thing, right? Really the same thing. Okay, so that's dissociations. Next, we'll do an equilibrium problem with an acid. In this case, we'll use acetic acid. Acetic acid has a Ka of 1.8 times 10 to the negative fifth. We'll get to Ka's in a minute, but a Ka is just an equilibrium constant for an acid. How much does it break up? So if you were to say you have something like a 0.100 molar solution of acetic acid, and you want to know how much of all the different species are in the solution, and therefore then after that we can calculate pH. You would have to first show the dissociation of acetic acid. Right, into the acid and base conjugate species. And then you set up your ice table. Right, you start with 0.100 molar of the acetic acid. None of this and none of this. And then you're going to subtract a certain amount. This is a 1-to-1 ratio, so you get x and x. And if you set up your K expression, then your Ka is 1.8 times 10 to the negative fifth. That's going to equal the products, x squared then, over the reactants, 0.1 minus x. Instead of solving this with the quadratic, we're going to make the assumption due to the small Ka value, the x is small. So you can just put it over 0.1 and ignore the x. And if you solve for x in this case, do it really quickly. You end up with an x value of 0.00134. Okay, now this is the value now of your hydronium ion, which means if you want to go the next step and calculate the pH of the solution, we'll deal with pH in a minute, but pH equals the negative log of the hydronium concentration. So what you're going to do is you're going to take the negative log of 0.00134. Let's do this here. And you end up with a pH of 2.87, which makes sense. That's a weak acid, right? But fairly concentrated solution of a weak acid. So that's a typical problem with equilibrium and calculating a pH. If you're doing it with the base, if you have a base and you're calculating equilibrium, you do the same thing. Then what you're going to end up doing is calculating a pOH value. And then later in this video, we'll talk about the relationship of pH and pOH. pH plus pOH is going to always equal 14. So if you subtract your pOH from 14, you'll get the pH. We'll get that in a minute. All right, now I want to just make some definitions. We already talked about what Ka is. Ka for any given acid is going to be the product. So if we have acid HA, whatever this acid is, the Ka will be, this is going to break up. You write the dissociation, you have something like that. So the Ka will be the products, which would be the hydronium concentration times the conjugate base over the original. Right. If you're looking at the Kb, now what I'm going to do is I'm going to show you the Kb for the conjugate base of this particular acid, and we'll show you how those two things get together in a little bit. So if I had A minus whatever this is, it could be any base plus water. Now I'm not going to write this thing backwards. I'm going to show the base, whatever it is, in water, and it's going to accept, right, the hydrogen from the water, and it will yield your OH. So in this case, your Kb would equal the conjugate acid over the concentration of the original base. You could also write this, you could, for instance, this could be just some base is going to grab a hydrogen, right, if you wanted, and sometimes you can see it written like this. Right, so you're doing your equilibrium problems similarly in both. All right. So those are the K values. Kw is the equilibrium expression for water. This is called the auto-ionization of water. So if you take water, right, water is going to break up into hydrogen and hydronium, or hydrogen and hydroxide ion. So one of the waters will give a hydrogen to the other one, and you will end up with this kind of thing. You can also write it like this. You could also write it like this, and it'll give you the exact same unit and value. Okay, so I'm going to keep it like this right now. So the Kw is going to be just whatever you have on top over. In fact, this is a liquid, right? So there's no substance on the bottom. So the Kw is just the hydronium times the hydroxide concentration. Now in any water solution, this number will always equal 10 to the negative 14th, right? Kw is 10 to the negative 14th. And in pure water, what will happen is the water will break up in equal parts hydronium and hydroxide. So you will have 10 to the negative 7 and 10 to the negative 7th of each in pure water at standard temperature. Which means if the hydronium concentration is 10 to the negative 7th, the negative log of 10 to the negative 7th is 7. This is your pH, of course, for neutral water. Okay? Good. Now we talked about pH as a negative log of the hydronium concentration. Right? pH equals negative log hydronium concentration. pOH is the exact same idea, but for the hydroxide concentration. So this is what pH and pOH are. And what a P does, taking the negative log of something, it takes a value and it puts it in a logarithmic scale. So it gives you whole number integers, which each represent a factor of 10. So if you were to take, I'll show you this in a table in a minute, but if you were to take something with a pH of 7 and you compare it to something with a pH of 6, this substance with a pH of 6 is 10 times as acidic as the pH of 7. Something with a pH of 5 is 100 times as acidic as the pH of 7, and so on and so forth. Right? Same thing as the Richter scale. Okay. One quick other value before we get into a few key relationships is pKa and pKb. Now, again, we see the P, which is just the negative log. The negative log of the Ka and the negative log of the Kb. This does the same thing. It puts Ka and Kb values in an integer scale, right? This logarithmic scale where every integer shows, a 10 times increase in the strength of an acid. This becomes important, pKa and pKb, a little later when we talk about things like buffers. But just so you know the formula. Okay. Next, before we conclude, a few key relationships. Here's the first one. Kw equals Ka times Kb of a conjugate pair. The reason why, earlier we showed that Ka equals the hydronium times the conjugate base over the original acid. The Kb we also showed for this particular acid, showed us the base, right? If it's going backwards, the base with water would yield, we'd grab that, right? And these would be the products times OH. So if you look at these two expressions for a conjugate pair and you add them together, let's put this one next to this one. We're going to look at HA so if you actually multiply these two together, what you'll notice is that the HA cancels on the top and the bottom, and the A cancels on the top and the bottom. So of course what you're left with is the hydronium and the hydroxide concentrations, right? Which of course equals the Kw. So this is very handy when you go ahead and make one calculation. You discover the Ka, for instance, and a question asks you, well, what's the Kb of the conjugate, or any question derived from that. Well, you can make this basic conclusion. Kw is always, of course, 10 to the negative 14th. So 10 to the negative 14th is going to equal your Ka times your Kb with the acid and base combination. Very helpful relationship. Okay. Another key relationship then deals with this, the pH and the pOH. So if I, for instance, am looking at, again, this Kw times OH. So this is the Kw expression. Let's take a look at these two things. This is always going to equal 10 to the negative 14th in a water solution. So if we make a table, make a little table of these values, and let's look at some other information. Let's look at the pOH and a pH. If I go down to the middle of this table, these two things together always have to equal 10 to the negative 14. So if I'm looking at equal amounts in pure water, I'm going to have 10 to the negative 7th and 10 to the negative 7th. The pOH of pure water is 7, and the pH of pure water is 7. Shoot. Has it been recording all that? Yep, I think we're good, hopefully. So anyway, when you go ahead through, the pH of pure water is 7, the pOH is 7. These concentrations are equal together, they multiply to equal 10 to the negative 14. If I make this an acidic solution and somehow I increase the hydronium concentration by 10 times, that means that to equal 10 to the negative 14th, this has to decrease by 10 times. So this will be 10 to the negative 8th. Therefore, this solution will have a pOH of 8 and a pH of 6. So we're moving up. Of course, 10 to the negative 5th corresponds to 10 to the negative 9th. So I end up with a pOH of 9 and a pH of 5. This could go to the negative 3rd, the negative 2nd, the negative 1st. So if I go all the way up to, like, for instance, 10 to the negative 1st, I'm going to have a pH of 1, very acidic. This correspondingly shrinks to 10 to the negative 13, give me a pOH of 13. And what you'll notice is that the pH and the pOH are always going to equal 14, right? So here's the key relationship now. pH plus the pOH are always going to equal 14 in a solution. And that will help you solve some problems as well. This little table also just shows you the logarithmic nature of pH and pOH. If I increase my OH concentration and I get 10 to the negative 6 here, then this of course has to be 10 to the negative 8. So are you going to have some hydronium in every solution? Yes. And notice the scale now goes above 7, which means you're in a basic range. You have more OH than hydronium. And in this case, you'd be a 6. Going all the way down, if this is a 10 to the negative 13th, very basic solution, 10 to the negative 1st. You can even go up higher. You could have a pH of 0, which would be like a 1 molar solution of hydrochloric acid, something like that, which would give you a pOH of 14. So they go all the way up and down. And they even can go to the negative values if you go push the edges. Okay, that's a long video. We'll see if any of this can load onto Moodle. And good luck with your problems. Let me know if you have any questions. Bye-bye.